Hello, welcome to another video on the basics of in Vivo NMR. Today we're going to talk about MR hardware and specifically RF coils. This is the second part on RF coils. If you're interested, there was a first video basically talking about the very basics of electronic circuits. Electronic circuits are an interplay between voltage, current and resistance. And many of the effects, the electrical effects, can be explained with electrostatic forces that will lead to the motion of electrons. The voltage provides an electric field, and then the associated electric force is propelling the electron forward, which then generates an electrical current. Resistance is a scaling factor between voltage and current, and it expresses the amount of energy that is required to push those electrons around the circuit. These electrons, they move at a drift velocity, and that is actually quite a small number. It's measured in millimeters per second. So electrons don't whirl around the circuit very fast. They actually move quite slow. They do have a random velocity, the Fermi velocity, which is a much higher number. However, this is random, so this can pretty much be ignored. Now, setting up the electrical field does go very fast. It goes 50, 60, 70% of the speed of light. So the electrical signal propagation is quite fast, even though the actual electrons move quite slow. And overall, an electric circuit can be seen as an energy conversion system in which the potential electrical energy due to the position of a charge in the electric field is converted to other forms like heat, mechanical, or radiant. Now, so far we've only been talking about these three components: voltage, current, and resistance. Now, is that enough to actually make a radio frequency coil? Now, to figure that one out, let's have a quick look again. What do we actually need to achieve? Right, so we have our magnetization along the z-axis, and that rotates around at the Larmor frequency. For the magnetization to coherently rotate to the xy plane, we need to have a magnetic field that is perpendicular to the magnetization, and that magnetic field needs to rotate at the same frequency. Then and only then do you get a coherent rotation of the magnetization. So an RF coil will need to generate a time-varying magnetic field B1 at or very close to the Larmor frequency during RF pulse transmission. Once the signal is in the xy plane, it starts to rotate at the Larmor frequency, and it will induce a voltage in potentially the same receiver coil. And we'll get back to electromagnetic induction in a minute. So basically, these two requirements, they cannot really be satisfied with constant voltage, current, and resistance alone. We will need to have additional and time-varying components to basically make a practical RF coil that can, with a rotating B1 field both during transmission and reception. So in the previous video, we've basically talked about electrical systems with constant voltage, current, and resistance, and that discussion was primarily limited to the electrical field inside the conducting wire. Now, to understand the effects of time-varying current and voltage, as we'll cover in this video, we will need to consider the generation of magnetic fields outside the wire. We will also need to know what inductors are and how they store energy in a magnetic field. We also need to know what capacitors are and how they temporarily store energy in an electric field. And then finally, it's the interchange of energy between inductors and capacitors that basically set up a system of time-varying voltages, time-varying current, and most importantly, time-varying magnetic fields, a B1 field that we can use as an RF coil. When these elements are tuned to the Larmor frequency, then we basically have a proper RF coil. Now, before we get there, we first need to kind of understand a little bit where magnetic fields are coming from. Right? We basically discussed last time that electrical fields that, for example, surround an electron is an intrinsic property of matter, just like mass is. And here we have an electron. The electrical field lines are shown as such. You as the observer are stationary, and the charge is also stationary. in this scenario, we know from the first video that there is an electric force, and if there's another electron, it moves under this force, which is given by the charge and the electric field. Now, what now happens if the electron starts to move, but you as the observer remain stationary? What you will see is you will observe a slightly modified electric field, and this has to do with a special relativity. If you're in a different reference frame than the electron is going to appear different. So the electrical field is going to appear different. At the same time, you're also going to observe a magnetic field surrounding that electron. The difference in this E prime and E basically is compensated by the addition of a magnetic field. Now, if there's now another electron here, that other electron will experience both an electric force, similar to the first scenario, but also a magnetic force. And that combined force is often referred to as the Lorentz force. And you can see here that it has an electric field component and it has a magnetic field component. But the magnetic field component is only relevant when the electrons are moving, when they have a velocity. If the electrons don't have velocity, then that second term is 0, and it basically defaults back to the electric force only. Now, this is of course a very qualitative description of magnetic fields. If you're interested in this, of course, there are some excellent papers, starting with Albert Einstein's paper, but Richard Feynman and one of the co-inventors of NMR, Edward Purcell, also has an excellent book on exactly these matters. What is important for today's video is that if you want to have a magnetic field, you need to have moving electrons. In other words, you need to have a current of electrons, and that will generate a magnetic field. If the electrons don't move, there will be no magnetic field. Okay, so let's have a look at a copper wire with electrons in it. The electrons run in that direction, and by definition, the current is then running in the opposite direction, as discussed in the first video. In this scenario, you will generate a magnetic field that surrounds the wire as such. Now, this can be very easily described with the so-called Biot-Savart law, which basically gives you the magnetic field at distance r away from a small line segment. Now, this may look complicated, but basically what this says is you just calculate the magnetic field from a small line segment, and then you can calculate it for any kind of arbitrary path by just summing these line segments together. If you have an infinitely long wire, it reduces to this expression. And so you can see that the magnetic field is directly proportional to the current in the wire. So twice as much current, twice as strong of a magnetic field, and it drops off as 1 over r away from the wire. Okay, now one more ingredient we need before we can actually start looking at some of the circuitry, and that is electromagnetic induction. So let's say we have a copper loop here, and there is a bar magnet. Now, if we now move the bar magnet, the magnetic flux lines through this copper wire change, and that will induce a voltage and a current. Basically, the electrons start to flow. The flowing electrons generate a secondary magnetic field, an induced magnetic field, that opposes the magnetic field that generated the current in the first place. So this is electromagnetic induction, where a change in magnetic field can lead to a current and an induced magnetic field. Okay, so now let's put things together in a circuit and see what we get. So this is the simplest we can have. We have basically a power amplifier providing us with voltage, and we just have a copper wire which has resistance in it. We have a voltmeter, so we can measure what the voltage supply is, and we also put a voltmeter over the resistor as well. And then we have an ampere meter to basically measure the current through the wire. Now, if we now close the circuit, and we basically supply the circuit with constant voltage, then basically the voltage over the resistance will be exactly the same, and because the current is the voltage over the resistance, the current will have an exact similar profile. Now, this was already all discussed in the first video. There are no surprises here. But now let's make things a bit more interesting. Let's add an inductor to that circuit. So an inductor is an electrical element that opposes change in electrical current. An inductor is characterized by inductance, and that is measured in Henry or millihenry or microhenry. So basically, if you have a current change, then that will lead to a time-varying magnetic field that induces a voltage in the inductor. And this voltage opposes the change in current that created it. This is Lenz's law, and therefore the combination of these two then reduces the change in current. An inductor stores electrical energy as a magnetic field when a current flows through it. And pretty much any material has some level of inductance, similar to resistance. So a straight copper wire will have some inductance, but you can also really emphasize the inductance. If you loop it like this and you make it into a small solenoid, that will have a much higher inductance than a straight copper wire. So you can definitely add inductance on purpose if you need to. So now let's add an inductor to our circuit as shown here. So now we have a resistance, we have our supply, and we have now an inductor. If we now close the loop and we provide this input voltage, what's going to happen is, of course, current is going to run, and then basically you're going to have an induced magnetic field that opposes the flow of current through the wire. So you're going to get an induced voltage inside the inductor that opposes the driving voltage. So here the driving voltage went from 0 to positive. Here the induced voltage goes from 0 to negative. And then on the other side it goes exactly the opposite. Now the resistor basically experiences the sum of both effects. And so you can see here now the resistor has a profile like this. And then the current follows that profile. So indeed you can see that the presence of the inductor basically leads to a slowing down of the change in current, right? If the inductor wasn't there, this was an instant rise, but because of the inductance, the rise is much slower. And then when you turn off the input, it will linger a little bit. It will exponentially decay. Now, and the exponential time constant is basically the inductance over the resistance. So this is one component that we need for our radio frequency coil. The second component is a capacitor. And a capacitor is another electrical element that delays the change in voltage. It is characterized by capacitance and is measured in farad. A capacitor is typically two metal plates that are parallel to each other and are separated by a non-conducting dielectric medium. And basically if you apply a voltage, you're going to get buildup of charge on one plate and a lack of electrons on the other plate, and therefore you're going to get an internal electrical field between the plates. And a capacitor stores the electrical energy as an electric field between the plates. You can have both self-capacitance and mutual capacitance, and these are how they are looking like. You can see on some of them kind of like a little bit the arrangement of some internal plates. So you can definitely add capacitance to a system by using one of these. Okay, so let's now see how that now looks. So here now we have a capacitor. Again, if we close the system and we drive it with this input voltage, the electrons start to flow and they start to build up on the bottom plate of this capacitor. At the same time, electrons flow away from the top plate. And this will continue until the voltage, the internal voltage difference inside the capacitor matches the driving voltage. At that point, the current stops and the voltage across the capacitor is basically the same as the driving voltage. The resistance basically has the voltage as the difference between these two, and therefore you can see that the current is only briefly on. In the beginning, when the electrons flow from this negative plate to this negative plate, there is a little bit of a flow. But when the internal voltage here is the same as it is here, there is no driving force anymore to propel the electrons, and so therefore the current stops. When you basically turn off the voltage, the charge is still there, so now the electrons start to flow in the other direction, and therefore you're going to get a negative current. Again, this is also with a time constant, and now the time constant is resistance times capacitance. Okay, so now how is this going to look like if we put it all together? So now we have a circuit where we have both an inductor and a capacitor. And let's say that our initial situation is we charge the capacitor. So at this point there is no current because the internal voltage in the capacitor is the same as the input voltage, and so everything is basically stationary. Now let's now close the circuit, so we basically remove the input voltage. At this point, these electrons on the bottom plate that are in excess start to flow. Electrons start to flow, and so the current goes up. That's the blue line goes up. The electrons flow through the inductor, generating a magnetic field and also thus an associated voltage. And so the voltage over the inductor goes up. In the same time, the voltage over the capacitor, because there's less electrons now on the bottom plate, goes down. Now this continues until the capacitor is completely decharged, at which point there is maximum current, and at that point all of the energy is now in the inductor. At that point electrons continue to flow, and now they're starting to build up on the upper plate of the capacitor. It builds up until the plate is fully charged, after which the process happens again, but in the opposite direction. So you can see here there is a continuous transfer of energy from an electric field inside the capacitor to a magnetic field in the inductor, and this goes back and forth and back and forth. And so you can see this makes up a natural frequency in which the electrons are moving, back and forth between the two through the circuit, basically making an oscillating current and voltage profile. Now, this has a natural frequency. A system like that has an inductor and a resistor, a capacitor and an inductor, basically has a natural frequency given by this equation. So it is indeed dependent on the inductance and the capacitance. Now, if we can make this frequency equal to the Larmor frequency of the nucleus spins, we might have something that starts to look like a proper RF coil. Now, of course, I ignored one aspect of this circuit. This circuit is of course made of copper wire, and the wire has a certain amount of resistance. So instead of this being going back and forth infinite, if there's no resistance, the resistance basically leads to a little bit of energy loss, and so over time the back and forth gets less and less and less as heat is lost over the resistor. Now, this curve is an exponential curve, and the time constant is basically proportional to the Q value of this circuit. And that is an important number because a higher Q value basically indicates it is a more efficient system. You lose less energy over the resistor. And so that will be a high Q value will be desirable to have this last as long as possible. This is the same curve. Some of the equations, so the Q value is given by all three parameters as shown here. Very often people don't look at the Q value in the time domain, but rather they go to the frequency domain. So you can do a Fourier transform of this, and you're basically going to get a Lorentzian line shape, where basically the Q is now basically the resonant frequency divided by the bandwidth that you measure at half maximum. Okay, now so why is this important? Well, you can nicely look at this when we're looking at a swing, a child swing. So if we run this video, you can see that if we push this swing once, you can see that it won't last forever, right? There is resistance on the mounting point, there's resistance with the air, etc., etc. So this will not last forever. Very similar to how the current in an RLC circuit doesn't last forever, right? But what now happens if we keep pushing it a little bit? So we're pushing it on every swing. And so now you can see is that you don't have to actually push a lot. You just have to give a little tap every time for the swing to get higher and higher and higher. In other words, the higher the Q value is, the less resistance there is, and the smaller this little tap can be to get a really large effect. In terms of an RF coil, it will be basically the higher the Q value of the RF coil, the less the input voltage needs to be for a significant B1 field to be created by that RF coil. So that's a simulation that is basically going to be shown here. So now this is a full RLC circuit driven with an input voltage. These are some of the parameters. So we have a certain resistance, certain capacitance, and certain inductance. With the equation that was shown on the previous slides, you can calculate that this has a natural frequency of 100 megahertz, and it has a Q value of a little bit less than 16. Now we're going to now drive this circuit with this input voltage, and this input voltage will have a peak of 1 volt. But now if you now look at the voltage, let's say over the capacitor, you can see that initially, that is 1 volt, but you can see that it built up over time. Very similar to that swing example, where small pushes at the right time will make that swing go higher and higher and higher. Same thing happens here. If the input voltage oscillations are at the same frequency, you're going to get this coherent build-up of voltage over the capacitor, and it builds up all the way up to the Q value, basically 15.7 volts over here. Now this is of course desirable because now with a very small input voltage we can generate a very large B1 field during RF transmission. Similarly, during reception, the circuit is now very, very sensitive to picking up small signals and amplifying that. So this amplification is called voltage multiplication, and that is a very desirable feature. Okay, so we're almost there, I think, for today's video. But there's still one problem, because so far we've been discussing this circuit as kind of like a free-floating circuit, but that is of course not realistic. We need to connect this at the very minimum to a coaxial cable that then needs to be connected to the rest of the system, right? So we need to at least have some copper wires like there and like there. And then, of course, we need to also take into account that we're going to basically add either human subjects or phantoms or whatever, something that loads this circuit. Now, there's a number of problems with this. So basically, during RF transmission, this coaxial cable is going to be connected to the RF transmit amplifier, right? You're going to get like power through this cable. Now, it turns out that it is important that the impedance, or the resistance, if you want to call it that way, of this circuit is the same as the impedance or resistance of the rest of the system. Now, the rest of the system is at 50 ohms, so ideally this would also be at 50 ohms. Now, if the empty circuit without the subject is at 50 ohms, then that's fine. But as soon as you add a subject to it, the resistance and the impedance will definitely change. So then you're going to have a different impedance for the loaded circuit and the system, and that will lead to inefficient power transfer. Another effect is, let's say that you're working at 100 megahertz line frequency, and the empty circuit is at 100 megahertz. But the fact that you now put a sample on there, that sample interacts with the circuit, it has its own resistance, inductance, and capacitance, and so that will change the natural frequency of the combined system. And so now you're going to have a mismatch between the Larmor frequency and the natural frequency of this system. So we need to deal with both of that, and that is done with so-called variable capacitors. So on the RF coil, the actual wire has some capacitance, but there's also so-called fixed capacitors, which are looking like this, and those have these parallel plates inside of them. But these are just fixed value. Once they are soldered in place, you cannot change them anymore. Here, this is a variable capacitor. They look a little different. You can see here, there is now a threaded screw here, where you can push it in or out, and that will change the capacitance value. And so we have a little bit of a range to deal with different samples. If we put a sample on there, we can change this matching capacitor to make sure that the resistance of the loaded circuit is at 50 ohms by changing this capacitor. Similarly, there will be another variable capacitor, the so-called tuning capacitor, and if you tune that, if you adjust that, you're basically making sure that the natural frequency of the loaded circuit is the same as the spin Larmor frequency. Okay, so that's the hardware. How would you do that in practice? Well, you would use a network analyzer or a sweeper or something like that. But basically, you're going to get a curve something like this. So here, of course, the horizontal axis is the actual frequency. But the bottom line here, typically, that is 50 ohms. So at the moment, this red curve, it is at the right frequency, let's say 300 megahertz, but it is not properly matched. There is a discrepancy between the phantom plus RF coil impedance or resistance and the system resistance, and so there is a mismatch. So tuning or changing that matching capacitor will basically make this curve go down. And when the dip hits the bottom, then at 300 megahertz, you have indeed an impedance of 50 ohms. So, great. Now you're going to put another phantom on there, or another sample, and now you're going to get this red curve. So it's immediately obvious that this red curve has now the wrong frequency, and again, it is not matched to 50 ohm. So now you have to change both the tuning and the matching capacitor, and you're going to basically be able to get the green curve. The tuning and matching, you have now the right frequency and it's matched again. Okay. Now you can see that the green curve is much broader than the blue curve, and the blue curve is referred to as the unloaded curve. That's the response of the coil when it's empty. The green one is when it is loaded with a phantom. Now, you do want to see this broadening because that indicates there is a good interaction between the phantom or the subject and the RF coil. So typically you want to at least have like a 2 or 3-fold broadening of this curve. Now, tuning and matching is not always necessary. I would say almost every clinical RF coil doesn't require tuning and matching because there are typically so many RF elements in it. It will take forever to tune that. Also, RF body coils are typically not tuned and matched either. Very often surface coils, multi-nuclear coils and home-built coils, they have tuning and matching circuitry. You can see here, these white cylinders are the tuning and matching capacitors, and these sticks here at the end are basically what allows you to change these values, and here is then the surface coil, for example. But what that does mean is that, let's say that you're using a clinical RF coil, and you cannot tune and match it, that means that it becomes your responsibility to design the phantom to be very similar to the human head. Very likely a human head coil is optimized for a human head size and load and the human head characteristics. If you're going to put a very different phantom in there, then the coil might not be tuned and matched properly, and you're going to get suboptimal results. So it's up to you to basically mimic the human head as much as you can with that phantom design. Okay, so just to wrap this video up, electricity and magnetism are two aspects of electromagnetism. Magnetism arises from moving electric charges and is a direct consequence of special relativity. Resistance is the opposition to electrical current. Inductance is the opposition to change in current, and capacitor is the opposition to change in voltage. Impedance, which I've been using it as a substitute for resistance. Impedance is a little bit more difficult. Basically, it combines resistance and some other aspects, which I think it's outside the scope of this video. So at the moment, I'm using impedance and resistance interchangeably. And resistance, inductance, capacitance circuit, or RLC circuit, has a natural circuit frequency as the energy is transferred from the electric field inside the capacitor to a magnetic field surrounding the inductor, and that goes back and forth, setting up that natural frequency. The Q value of this circuit is important because the high Q value basically indicates low energy losses, and so therefore you need to have a much lower driving voltage to get large effects. That will translate in an efficient RF pulse transmission and high detection sensitivity. And then many research RF coils, they have variable tuning and matching capacitors to make sure that the circuit has the proper resonance condition, and that the resistance or impedance is properly matched for a given sample. Okay, so that's what I wanted to cover in today's video. I think there's one more video after this where we're really going to talk about the practical aspect of using RF coils. I hope that you'll watch that video as well. Okay, thank you.